In order to try as best as we can to stay to time this afternoon, I think we'll kick the session off. So bienvenue and thank you. It's my great pleasure on behalf of myself and my co-chair to welcome you to this afternoon's session on biosignatures and clues of life. And as you'll see, if you've looked at your program, we have quite a range of topics that will be represented here this afternoon, ranging from the earliest record of life and origins of life on the early Earth to Earth analogs, astrobiology and life detection, and studies of Enceladus and Mars. And so it falls to me in the first few minutes to just try and provide a bit of contextual introduction to all of that. And I've chosen to do that by talking a little bit about some of the complementary advances in biosignatures and prebiotic chemistry, and indeed what we might call abiosignatures, and to do that by drawing on a couple of examples from the literature, including some of the work that we do ourselves at the University of Toronto in Canada. And so a good jumping off point for the first example is indeed some of these reports of methane in the Mars atmosphere. And the main point I want to make here is, regardless of what the eventual outcome or verification of these results are, this has really launched an important progress in terms of thinking about the use of biosignatures to try to resolve the origin of methane. And indeed, if you take a look at the literature and some of the discussion of the variety of potential processes that might contribute to methane in the Mars atmosphere, those range, of course, from both biological to geological. And within the geological or abiotic, there's initially much discussion primarily of high temperature sources, either related to volcanic activity or hydrothermal activity. But what I'd like to focus on as well is a second category of processes that's been discussed as well, and that is the potential of gas production from more low temperature range of processes, and specifically low temperature in the geologic context, meaning less than maybe about 150, 100 degrees Celsius. And those are low temperature processes then of water rock alteration, sometimes referred to as WRI, water rock interaction. And in fact, there's a wide variety of them, but one of the ones that's of course caught the real imagination and under much discussion these days is this reaction referred to as serpentinization, which refers to the hydrothermal, or sort of to the alteration of ultramafic rocks, and has as a byproduct of that reaction substantial production of hydrogen gas, and through associated reactions sometimes production of methane as well. And so this is a category of abiotic or geological reactions that have really come to the fore as a result of some of the work that's done in terrestrial analogs, both at the hydrothermal vents, but I'm going to focus in particular on some of the work that's taken place within a different kind of terrestrial analog, and specifically one in which, amongst other groups, we happen to work, which is work in the deep Archean or deep Precambrian rocks of this planet, and specifically accessing those deep subsurface environments by mines, and we do that both in Canada and Finland and in South Africa, and specifically within those environments investigating the origin of methane, the origin of hydrogen, but specifically the relationship between the production of those gases through low temperature water rock reaction with chemoautotrophic microbial communities that have been identified in the very deep subsurface of the Precambrian shields in groundwaters at 2 to 3 kilometers depth. Now, I think the most familiar work in this area has really been within the gold mines of South Africa, where we've been working with our colleagues at the University of the Free State, with Princeton and Indiana. But in fact, one of the reasons why I think the work within the gold mines of South Africa in particular has caught people's attention is because of these two papers. These were papers published on the microbial communities identified in those waters. And specifically, they're both from the same site in South Africa, the Manompeng mine, and they describe communities that were discovered in the groundwater there at 2.8 kilometers depth. These are chemoautotrophic communities that couple the utilization of hydrogen to sulfate reduction. But what was really exciting about them is not only that these were some of the deepest communities yet identified on the planet, but specifically that not only were these very low biomass communities, but they were in fact very low biodiversity. And in fact, the Chivian et al. Paper referred to this as a potentially single species ecosystem. But again, the point I want to make is that this is by no means the only site of this kind. This is just one of dozens of sites within South Africa at which we've been working. And indeed, The geology, Precambrian shield rock, is present not just in South Africa, but in fact at sites all over the world. So it's important to emphasize then, you may be familiar with the work done in South Africa, but this is really just one site in a network of sites that are represented in the Precambrian shields throughout the world. And indeed, these are ancient cratons, of course, some of the most oldest rocks on Earth at 2 to 3 billion years in age. Unlike the kind of analog work that takes place at the hydrothermal vents, these are, of course, tectonically quiescent, cool, continental settings. And we know this from noble gas work that's been done, showing us that in the present time, there's no significant magmatic or volcanic component within these kinds of systems. These are continental, crustal systems dominated by radiogenic noble gases. Like the hydrothermal vents, however, the groundwaters that we find within these crystalline rocks are dominated by the processes of water-rock reaction. Although, of course, within these lower temperature environments, these are reactions taking place at much slower rates. However, what they have is very long timescales. So again, these are crystalline rock of very low porosity and permeability, but there are significant waters in them, but they're waters that are constrained within fractures within the crystalline rock. And here, they have very high salinity and highly altered delta-18 and deuterium signatures that indeed indicate that these are the products of water-rock reaction, accumulating in these hydrogeologically isolated fracture networks over geologically long timescales. This we know from, again, from noble gas work, which has given us bulk residence time estimates for those waters on the order of millions of years. My own area of research deals with the dissolved gases present in those groundwaters, and I just want to very quickly show you in one slide the results of about 10 to 15 years worth of work. Essentially, the photos are here to show you that this is very much a macroscopic phenomenon. Although these gases are dissolved in the groundwater, when the fractures open, you have significant exsolution of those gases. In some cases, release of gas bubbling on the order of 30 liters of gas per minute from a single borehole. So it's very much a macroscopic phenomenon. As I've mentioned, the gases are primarily composed of methane, but with significant components of higher hydrocarbon gases as well. And again, I alluded to the fact that these are very hydrogen-rich. Particularly at the ultramafic sites, we see concentrations of dissolved hydrogen up to 10 millimolar, making these, like the hydrothermal vents, some of the most hydrogen-rich environments on Earth. And essentially, over the course of working at dozens of sites on 3 continents, over about 15 years, the following interpretational framework has been developed. Essentially, we see evidence for 2 major types of gases and fluids. At many of these sites, we do see the evidence of the action of these microbial communities. And particularly with respect to methane, at many of these sites, we do see that the methane is produced by microbial methanogenesis. So the microbial communities are coupling hydrogen utilization, not just to sulfate reduction, but also to methanogenesis. But what I want to speak to you about primarily are the deeper sites in particular, deeper within these systems, where we see in these cases, we do not see the evidence of microbial contribution to the hydrocarbons, but instead see hydrogen and hydrocarbon gases that are the products of these kinds of low-temperature water-rock reaction. This has all been published, so I'm not going to go through this in great detail. But the key point I wanted to make is why on earth would it take us 15 years to come up with this interpretation? And the main point I want to make, it's because we do know a lot about biosignatures of hydrocarbons. We know largely what a biologically produced methane or hydrocarbon will look like. But when we began this work, the same was not true about what I might call abiosignatures. In other words, this whole category of low-temperature water-rock reactions, we knew almost nothing about what the gases would actually look like coming out of these kinds of reactions. And again, I'll clarify, this again are not a magmatic or volcanic-driven system. So we're not talking about magmatic methane. We're talking about hydrocarbons and hydrogen produced by these low-temperature reactions. And so it took about 10 to 15 years worth of the development of a subfield that's quite complementary to the prebiotic chemistry that's represented here in today's audience. Essentially, a lot of work done by various different groups looking at various abiotic organic synthesis and characterizing both the composition and the isotopic signatures of the gases produced by that category of reaction. And essentially, one of the key points to come out of that is to see that the methane produced by these kinds of organic processes can be consistently depleted in delta C13 by up to 30 to 40 per mil, meaning that the presence of a depleted carbon isotope signature on methane is simply not a sufficient biosignature. that abiotic processes can similarly produce very depleted carbon isotope signatures. And so an evolution of the field to understand that isotopic signatures alone are insufficient for resolving abiotic versus biotic origin of methane or other hydrocarbons, and an increasing focus on this idea of integrating isotopic signatures with multiple lines of evidence, and an increasing focus on the need for looking at associated gases as well, and in particular contextual evidence from the geology and the hydrogeology. And so indeed biosignatures work, of course, on origins and evolution of life and on paleoenvironments, rapidly evolved our understanding of biosignatures. What we've seen over the last 10 years is a recognition that if we're going to actually recognize life, either on this planet or elsewhere, knowledge of the abiotic baseline is also necessary. And in particular, we've seen what I think is some very nice complementary developments between biosignatures and prebiotic chemistry that's well reflected in the, this joint meeting, I think, that's taking place here this week. In the last couple of minutes available to me, I just wanted to make one further point about the kinds of insight that's coming out of taking a look at deep subsurface life on this planet in Precambrian shield rock, and what that is telling us that might have important implications for our studies of the origin of life and bioastronomy. And that comes down to this issue of habitability, which of course we all discuss in terms of this idea of the thinking that habitability is really dependent to a certain extent on the presence of liquid water. But the point I want to make is that there's another aspect to that issue of habitability, and one that we all know but perhaps don't think about quite so much, that I think is nicely represented by this slide, and that is habitability is really dependent not just on the presence of liquid water, but on the potential for that water to flow and mix, a concept, of course, referred to as hydraulic conductivity. And just to illustrate then the changes in hydraulic conductivity on a very gross scale, in marine sediments or surface sediments that are dominated by porous media, groundwater flow takes place between the interstices, between the mineral grains, by the physical processes of advection and diffusion. But of course, as we go deeper into the Earth, or indeed into the subsurface of Mars, into crystalline rocks, we have a substantial change in the physical parameters that control groundwater flow. We move out of a zone that's dominated by advection diffusion between the porous media grains, and we move into systems that are dominated by fracture-controlled flow. And indeed, as we go even deeper in these systems, and pressures close off those fractures one with respect to another, or they're closed off by precipitation of fracture minerals, this kind of a hydraulic conductivity becomes even more limited. And one ends up with a distribution of groundwater that is much more patchy and irregular on both a spatial and a temporal scale. The implications, of course, for life is that the distribution of life in such systems must also be patchy and irregular. And indeed, the key point I want to emphasize is the more we investigate these deep Precambrian shield groundwaters, the more we see that these hydrogeologic discontinuities serve as virtual time capsules. And I'm just going to take one clicked slide to illustrate what I mean by that from a recent paper that our group has done from South Africa yet again. In this case, you might sort of tongue-in-cheek call this the world's oldest water. But the key point is, again, this is from the Witwatersrand Basin, from dozens of these sites. But it does indeed also include data from this site at which the very low biodiversity microbial ecosystem has been identified. Again, I'll remind you the bulk fracture water residence times are on the order of tens of millions of years. But what was really exciting about this paper is that we were actually able to identify certain components of that groundwater, specifically the neon, that's in fact much older and derived from remnants of actually Archean age fluid, and most specifically due to leakage of fluid inclusions into the bulk groundwater. What's significant about this is that this kind of hydrogeologic isolation that we find in these systems means this is one of the very first times that a significant component of leaking fluid inclusions has been identified in an overall fluid. And again, it just speaks to exactly how isolated these hydrogeologic systems are, and the very high rock-to-water ratio means that these components of water-rock reaction or fluid inclusion leakage contribute a major component of the bulk groundwater. In terms of this implications for origins and bioastronomy, it's essentially this. These provide us with literally time capsules of terrestrial life. These are fracture networks, as we've seen, accumulating products of extensive water-rock interaction and leaching, and the most deep part of these systems very hydrogeologically isolated, with Bulk groundwater times on the order of millions of years, but some components more than 2 billion years in age. And again, this kind of information or context from the geology and the hydrogeology is what has allowed us to identify that, in fact, these microbial organisms have been cut off from the photosphere on such extensive timescales, meaning that they're some of the most isolated microbial ecosystems yet identified. So obviously, important targets, both for investigation of the origin of life on Earth and evolution, but also when we move to bioastronomy, because they do speak to the ability for life to continue to survive, even very deep in the subsurface, in some of the world's most ancient crystalline rocks. And so important analogies then for exploration for life on other planets. So with that then, I'd like to introduce our very first talk for this afternoon's session, Emmanuelle Javois from the Université de Liège en Belgique, and she's going to speak on indices of life, lessons from the early Earth microfossil record.